Hi, welcome to today's video about artificial intelligence, AI in chemistry. This was a big success in 2020, that's project AlphaFold 2. This is about predicting the structure of a 3D molecule with the help of AI. You can see in this picture three big complex molecules. In green, that's the experimentally found structure. In blue, that's the predictions of the AI AlphaFold 2. This matches nicely with very little exceptions. For example, here's a little difference. So this was tested on 87 protein domains. Protein domain is a part of a protein with a specific function. And this produced a high accuracy results. For a big 3D molecule, there are conformations, 3D structures, and that can reach a number of 10 to the 300. For comparison, the number of the atoms in the universe is between 10 to the 78 to 10 to the 82. This is how AlphaFold 2 did it. That's the architectural details. At the top, that's the MSA, multiple sequence alignments. The AI does the same as a human would do, breaks down this big problem to many little problems. And then there's a evoformer, which makes update operations in each block. In D, that's the structure module. Here is the residue gas. And this picture F is the frame alignment point error. This is the green structure as the predicted structure, and the true structure is in gray. This is an overview of Blue Obelisk projects. Blue Obelisk is a group of chemists who promote open data, open source, and open standards. One is this QSRA. QSRAR, quantitative structure and activity relationships. This is about the structure of a molecule, its relationship with properties. For example, HOMO-LUMO orbital energies. HOMO is the highest occupied molecular orbital. LUMO is the lowest unoccupied molecular orbital. Or the bioactivity, or the toxicity, or the solubility, melting point. And another project is OpenSmiles. This is OpenSmiles. It was developed in 2007. That's a simplified molecular input line entry system. In this picture, you can see as example, ciprofloxacin, which is an antibiotic. The carbon cycles are broken and labeled as branches of a backbone. You can see it here. This gives you the simplified structure. The advantage is you get a compact data structure, and disadvantage is there's no information about the stereochemistry, that's the 3D structure of the molecule. This is an overview of deep learning for molecular design, which is a subset of machine learning, and this is a subset of artificial intelligence. Deep learning is a technique to perform machine learning inspired by our brain's own network of neurons. So this is about training a deep learning algorithm with known molecules that have special properties. Then the AI will generate new molecules of interest. They can then be synthesized or can do a virtual screening, find the best molecules for further development. This is called Bayesian optimization. It's a sequential design strategy for global optimization of black box functions. It's a Gaussian process. This is shown in the top picture in purple. You can see with each round, model gets better and better, and this can be used to find the optimal molecule for a specific set of properties. This is one molecule, discodermolite. It was isolated in 1990 from the Caribbean marine sponge, Discodermia dissoluta. They used a sample of 434 grams of sponge that were isolated for the isolation of 7 milligram of this compound. This is a light-sensitive compound, so the sponge had to be collected from a depth of 33 meters or deeper. What's special about this compound is that it stabilizes microtubules. It inhibits growth of tumor cells. At the right, you can see the analysis for the retrosynthesis. This compound, retrosynthesis means finding ways to synthesize these molecules. And this kind of work has a big potential for artificial intelligence. This is an overview of how the Monte Carlo tree search algorithm works. It has 4 stages. That's the selection, expansion, a rollout, and the backpropagation. This algorithm was successfully used for the games chess and Go. It is also efficient for simple molecules. However, for complex natural molecules, there's a lower number of natural product synthesis in the literature that you can use for training that lowers the quality of the AI results. To give you an example, for this compound discodermolide, there's a minimum of 21 total synthesis steps, and the AI also is not able to predict the correct stereochemistry yet. And this interesting compound, that's Yugi's amine, that's the compound at the left. That's 1-dimethylamino ethyl tyrosine. It was synthesized in 1970 by Ivar Yugi. You can use it for stereoselective lithiation with N-butylithium. This gives you either R and S diastereomers depending on the reaction conditions. In this picture here you can see this methyl group does not want to be on the side of the aromatic rings. It prefers this structure where it is away from the aromatic rings. But you can make both of these compounds by controlling the reaction conditions. This is a simplified model of a thermally agitated molecule. The Monte Carlo tree search can also be used for the design of new catalysts. The answer from each node is passed to the child nodes. For example, what are the top 3 best catalysts, which are low cost, which have the highest activity. So you can optimize your model step by step. This is the principle of convolution. That's a mathematical operation on 2 functions, f and g, that produces a third function. This picture that's in cyan color. A graph convolutional neural network mode can predict the major product correctly in over 85% of the time in 100 milliseconds. The AI can predict solvents, reagents, catalysts, and temperatures that are optimal, but not yet the concentrations or reaction times. And it was trained on 10 million chemical reactions, which is a very impressive number. This is the aluminosilicate catalyst zeolite. You can use deep reinforcement learning to check all of the possible 160,000 unary, binary, and ternary compounds of 55 chemical elements. And one important feature of a catalyst is the absorption energy. It can't be not too high, but nor too low for a good catalyst. And this is an inverse design from the first principle, and this research is at the early phase. This is a nice movie of 50 micron hollow glass particles. You can use a deep learning model to find the best reaction conditions. For example, the best selectivity, productivity, energy efficiency, or the quality of the byproducts. This is a nice picture of a metallic glass. The metallic glass is an amorphous metal or alloy with glass-like structure. One example is vitriol 4. That's a picture of this compound. This is an alloy of zirconium, titanium, copper, nickel, and beryllium. And a dataset of 6,780 results from this field was used for machine learning. The AI gave new predictions that were tested in the experiments. The results were used to refine the machine learning model, and this led to a faster development of new metallic glasses. This is an interesting chemical reaction. That's the Suzuki-Miyaura reaction. The principle of this reaction is a new carbon-carbon bond is formed. You need a palladium catalyst and a base. This is the cross-coupling reaction of an organoboron compound. In this picture you can see how this works. The organohalogenide compound is added to the palladium complex. L is the ligand, and the halogenide is replaced by butylate. The next step is addition of the organoboron compound, and you get this intermediate compound. And in this step, the new carbon-carbon bond is formed, and you get your catalyst back. Important parameters are the electrophile, the nucleophile, the ligand, the base, and the solvent. And you can use an AI agent to analyze existing websites for reaction condition recommendations. These are the fields where you can use AI, and all these fields are growing exponentially. This is analytical chemistry, industrial chemistry, physical chemistry, energy technology, biotechnology, food, inorganic chemistry, material science, organic and polymer chemistry, and also pharmacology. And in the near future, there will be a tsunami of new knowledge coming. This is a nice picture of the Monte Carlo casino. It was opened in 1856. This is not only a casino for gambling, but also a complex with opera and ballet. And what's special about this building, or this complex, is the first Women's Olympiad was held at the Monte Carlo Casino Garden in 1921. If you're interested in artificial intelligence, I can recommend a great science fiction movie. That's the movie Lucy with Scarlett Johansson. Check it out if you're interested. That was today's video about AI in chemistry. You can check out the links in the description fields to the scientific articles. Thank you for watching. Have a nice day. Bye-bye.